Screen visible?
Ma'am, visible.
Okay. So in the yesterday's class, we were discussing something about how we are going to place the data which is present in the main memory into the cache memory. So that can be done using the mapping functions. And first, I had given introduction about the mapping function here. That is about the direct mapping. So if I consider 128 blocks in the cache memory, and if I consider uh, uh, 2048 words in the main memory. Okay, if I consider that way, means the main memory has 64k words, which will be 4k blocks. It is 4k blocks in the main memory, and it is 128 blocks in the main memory. In main memory and in cache memory, both each row is containing 16 words each. Okay, then that time first the direct mapping. How we are going to map? See, mapping means what? We are storing the same data which is present in the main memory into the cache memory, because to access the data very fast we are doing like this. But in which block of data? Suppose this block 0, where this block 0 is present in the cache memory, we have to understand, is it not? For that purpose we require the mapping functions, and in the direct mapping straightforward formula is used, that is j modulo 128. So block J of the main memory is stored in J modulo 128. Mod operation, what it will do? It will find the remainder. Suppose let me take J as 0. Block 0 of main memory, where it is stored in cache memory? So 0 modulo 128. What is 0 modulo 128? Mod means it is giving you the remainder. What is 0 divided by 128? What is the remainder? Yes, what is the remainder? It is 0. Okay, it is 0. Next, we are going for 128 mod 128. See, block number 128 of main memory is where stored where? So 128 mod 128. The remainder is 0. 128 get cancelled and remainder is 0. Next, we are going for block 256. 256 divided by 128. What is remainder? 128 2s are 256. So there is 0 remainder. So block number 0, block number 128, block number 256, and so on. All these are stored in the block number 0 of cache memory. Okay. So all these blocks, block number 0 of the main memory, block number 128, and block number 256. All these three blocks will be stored at block number 0. Next, coming to block number 1. What is 1 modulo 128? What is 128 here? 128 is the size of the cache memory. Number of blocks present in the cache memory is 128. And what is 1? 1 is the block number in the main memory. So 1 mod 128. What is the remainder? It is again 1. Next, 129 mod 128, remainder is 1. Or 257 mod 128, remainder is 1. So block number 1, block number 129, and block number 257 of the main memory are stored in block number 1 of the cache memory. So like this formula is followed, and the formula is followed, and the blocks of the main memory are stored into the cache memory. Then how do we access? Next question is, how do we access each block? So we are having an address which is generated by the main memory. So in this main memory, one address is generated. So 7 plus 4 11, 11 plus 5 is 16. So 16-bit address is generated by this main memory. These 16 bits are divided into 3 parts. So the first lower 4 bits determine which words. The lower 4 bits determine which word. There are 16 words in each of the row, is it not? There are 16 words in each of the row. Out of those 16, which word I have to select? Out of those 16, which word I have to select? That is understood by using these 4 bits. Next, coming to the block. See, in the cache memory there are so many blocks. Out of these so many blocks, which block the data is present, that is given by the 7 bits. 7, see, these 4 7 are the bit number. They are the bit number. 7 bit address. Next 7 bit address is telling you among all the 128 blocks, which blocks I have to select. That is told by this 7 bit address. Next, the higher order 5 bits is for tag. What is tag now? Each of the block is having its own tag here. Tag for identification. See, here also block 0, here also block 0 we are having. Block 1, here also block 1. Block 127 here. See, numbers are the same. Then which block I have to use? That time we are going for the tag. Tag is a special unique identification number which is given to each block in the cache memory. Tag is given in the cache memory. While generating the address in the main memory, see, block 255 is not matched with block 255 here. Block 255 of the main memory is matched with the tags here. Is matched with the tags. So, which tag is matching? Inside that we are going to search for that particular data. Understanding here how we are storing the, or how we are mapping the data from here, from main memory to the cache memory? Just we are using a jmod jmod 128. So like this we are using the data here. Then using the memory address of how much 16 bit memory address is generated. How is that 16 bit? So for the lower order 4 bits, these are to identify which word among the 16 words in each row. Next 7 bits are used for identifying which block I have to store the data into, and fifth 5 bits of this tag is matching the cache memory and the main memory block number. Like this we are doing. So what is the advantage here? This is very simple. Just using very one simple formula, that is jmod 128. We are going to using this small formula jmod 128. We are going to store the data. But what is the disadvantage here? Many of them are matching to the same block, is it not? Many of them are matching to the same block. They may create the rush, or they may create the contention in a single block. Now as I told you, block number 0, block number 128, 256, many others, they are matching only to the 0th block. In this 0th block there may be more number of contention. So this is happening, okay, in the direct mapping. To avoid this, next we are going for the associative mapping. What is this associative mapping? Is any block of the main memory sorry, any block of the main memory can be mapped anywhere in the cache memory. So 0th block can be mapped in block number 127 of the cache memory. Block number I can be mapped in block number 1 of the cache memory. Block number 4095 can be blocked in some block number 38. So like this you can map anywhere, okay, depending upon how the space is available. Depending on how the space is available, you can map the blocks of the main memory into the cache memory here. So now here same thing, mechanism is the same. We are using a block memory, we are using the main memory's block and mapping into the cache memory, whichever is free to that block we are mapping. Then how we are going to find now? We are finding by using this one. Here also 16-bit main memory address is generated, but here only we are having the 2 partitions. Each row is divided into 4 16 words. So among those 16 words, which word I have to select? That is stored by the last lower order 4 bits. Then the remaining 12 bits is nothing but the tag here. Since we are not having like any formula here, each block can be stored in any other block, is it not? Each block of this main memory can be stored in any other block. So that is why what we are doing here is 12 bits of tag is there. Directly the block number of this main memory is matched with the tag here. So using this we are doing the mapping in the associative mapping function. In the associative mapping function, what is happening here, you can see the main memory block can be placed into any cache block position. Okay, it can be placed in any block of the position, so the space in the cache can be used more efficiently. This is the main advantage here. A new black block has to be brought into the cache memory and has to replace an existing block only if the cache is full. So now here what was happening in the direct memory, suppose if only block number 0 is full, when block number 0 is full and some block from this main memory is again mapping to block number 0, other blocks are free, but still I am wanting to free this block number 0 only because of the formula used. This disadvantage is overcome in this associative mapping. Only if the complete cache is full, then only we are going to replace the blocks. Otherwise, wherever the place is free, wherever whichever block is free, in that block we are going to map the main memory block. So this is the associative mapping. More improved version of this is set associative mapping. What is this set associative mapping here is, so main memory remains same. Main memory is remaining same, but there is a change in the cache memory. What happens here in the cache memory is we are going to group different blocks and make one set. Now here two blocks are grouped and made one set. Two blocks are grouped here and one set is made. So set 0 is containing two blocks, set 1 is containing two blocks. All the sets are containing same number of blocks. So this is called as n set associative method. N set, n indicates the total number of blocks in one set. There are how many blocks here? Two blocks are there. So it is two-way associative method. Okay, this is two-way associative method where you are going to group the blocks into some sets here. Two blocks are grouped and we are going to map the functions. So what is the address generated here? So the address generated, last four blocks remains same. The lower order 4 bits are used for what? They are used for selecting a particular word from 16 words. What are these 16 words? Each row is containing 16 words. To represent 16, how many bits are required in the binary? To represent 16, how many bits are required? 4 bits. Is it not 1111? 4 bits are required for representing a 16. So all the time 4 bits. See, in n set associative also 4 bits are used. In associative also 4 bits are used, and in the direct mapping also 4 bits are used. So this is fixed. Why? Because I told you that there are 16 words in a row. When there are 16 words in a row, to select any one word we require 4 bits. Okay, we require 4 bits. This remains the same. Next, 6 bits are used for generating the set number. Out of set 0, set 1, set 2, which set to select? To select that, we are going to use the 6 bits for selecting the set number. Then the higher order 6 bits are used for again tag. So what is this tag? As I already told you, to match this to match the block of the main memory to the cache memory, we are going to match this tag here. Okay, block 0 same, but the contents are different. So how to match them? We are going to match using the tag. Block 0 will be having some tag. That tag and this tag, they are matching. So tag is used to identify a particular block from the main memory which is stored into the cache memory. This is the most efficient method among all the mapping functions, that is n set associative or set associative method for mapping the blocks of the main memory into the cache memory. Understood all of you? Yes, please tell me, have you understood or not? Reply from chat box. Have you understood? If you are having any doubts, you can ask me. Please reply, students. Have you understood? Okay. So next, moving on, we are going for next method, that is a replacement algorithm. So what is this replacement algorithm now? See, whenever I told you that this block contains block number 0, block number 128. Suppose the cache memory is full now. So when the cache memory is full, what happens? When the cache memory is full and the processor requires some data that is not present in the cache memory. When the cache memory is full, the processor requires some data which is not present in the cache memory. What will happen? It will become a cache miss. Cache miss means the data is not present. The data which is required, it is not present into the cache memory. So when the data is not present in the cache memory, what we are going to do? We are going to search for the data in the main memory, bring that data into the cache memory, copy that data, same data into the cache memory, and then give it to the processor. Is it not? So this is how we are going to store the data which is not present in the cache memory. But now cache is full. So when the cache is full, you have to replace some block, you have to send back to the main memory. Then you are going to store the new block. Which block is to be selected? Which block is to be selected for replacement? So that is done using these replacement algorithms. Generally there are many replacement algorithms used, like first in first out. The first in first out means what? The block which has come first into the main memory will go first out. Suppose the block is having only place to store 4 blocks. Okay, cache memory is having to store only 4 blocks. So block number 1 come first, then block number 2, then block number 3, then block number 4. Suppose now if processor is requiring block number 5, is the block number 4 present into the cache memory? No, only block number 1, 2, 3, 4 are present, but block number 5 is required now. Is there space to store the new block in the cache memory? No. Since the cache memory is storing only 4 blocks, all 4 blocks are full. Then what I have to do? I have to bring that block number 5 into the cache memory. For that, I have to replace one block from the cache memory into the main memory. Is it not? That time first in first out means who has come first? Block number 1 has come, so block number 1 will be replaced, then block number 5 will be brought. This is one method, that is first in first out method. This is very simple for implementing. Another method we are going to see here is least recently used sorry. Another method we are going to see here is least recently used replacement algorithm. Name itself is telling least recently used. Now block number 1, 2, 3, 4 are there in your cache memory, but block number 1 is used more. Block number 1 is used more times. Block number 2 is used less than block number 1. Like for example, block number 1 is used 4 times. Block number 2 is used 3 times. Block number 3 is used 3 times. Block number 4 is used only 1 time. Even though block number 4 has come now, but it is used only once, which is least used. Block number 1 is least used, is it not? So, sorry, block number 4 is least used. So, block number 4 will be replaced. Least recently used means what? Overwrite one that has gone the longest time without being referenced. Means that block is present into the cache memory, but it has not been used for long time. It is used for least amount of, it is referenced for least times. So such block you are going to replace. Least recently used means the block which is been present in the cache memory for longer time and is used very less. It is used least, you can say. It is used least. that block will be replaced in the least recently used algorithm. How it is replaced? Let us see now. Here one method they are following. So now let us take 4 blocks only. Okay. It is required to track the LRU block of a 4 block set in a set associative cache. Means what I told, in a cache memory there are only 4 blocks. Okay, in the cache memory there are only 4 blocks. 0, block number 0, 1, 2 and 3. 0, block number 0, block number 1, block number 2 and block number 3. Only 4 blocks can be stored in the cache memory. And to represent 4 blocks, how many bits we read? 2 bits. 0 0 is 0, 0 1 is 1, 1 0 is 2, 1 1 is 3. Like that. 4 blocks we require for 2 bits we require for representing a 4 block. Then the block which is referenced, okay, please pay attention here. The block which is referenced, its counter value will become 0. Okay, each one of them will be having a counter. Each 4 blocks will be having a counter. The block which is referenced will become 0. What about other blocks then? Other blocks whose value was originally less, whose block was originally less, that blocks will be increased by 1. Let me take an example here now. All of you, if you are having paper and pen, you can write down as I am saying here. So there are 4 blocks: block number 0, block number 1, 2 and 3. So we are having 4 blocks. Next, block number 0 is used for one time. Block number 1 is used for 2 times. Please write down as I am saying. Block number 2 is used for 3 times and block number 3 is referenced for 2 times. Okay. So block number 0 1 time, block number 1 2 times, block number 2 3 times and block number 3 2 times. So this is how we are going to okay. So what I am having here? So block 0, we are having block 0 is referenced for how many times? 1 time. Okay. Next, see in the chat box. So block number 1 is referenced for 2 times. Okay. See in the chat box again. Next, block number 3, block number 0 1 I think 2. Block number 2 is referenced for 3 times. Okay. Next, block number 3 is referenced for 2 times. Getting? All of you are seeing this one? Yes. So this, see, block number 0 is referenced for once. Block number 1 is referenced for 2 times. Block number 2 is referenced for 3 and block number 3 is referenced for 2. Now, suppose among these 4 blocks, block 0, 1, 2, 3, block number 3, block number 2 will be referenced. Next time, block number 2 will be referenced. So when block number 2 will be referenced, its counter value will become 0. Its counter value. So block number 2, block number 2's counter value will become 0. Now, why it will become 0? What I am saying here, whenever a block is referenced, its counter value will become 0. Next, what will happen to others? Others whose original value are less than the blocks. See now, block number 2's value was 3. Originally it was 3. Is it not? Originally it was 3. Now, whose values are less than this 3? Block number 1 is 2, it is less. Block number 3 is 2, it is less. Block number 2, block number 0, it is 2, it is less. So what it is telling? The original value is 3. Those whose counter values are less than this 3, increment them by 1. So block number 1 will become 3. Okay, block number 1 will become 3. Next, block number block number 3 will become 3, block number 0 will become 2. Understanding? Increment the values of all those blocks whose values is less than this one. 3. 3 is the reference value of block number 2. Who are less than 3? Block number 0, 1, 3. Block number 0, 1, 3 all are less. So increment them by 1. Block number 0 was 1, it will become 2. Block number 1 was 2, it will become 3. Block number 3 was 2, it will become 3. So like this you are going to increment. Okay. Now you have incremented. So what are the new values now? Block number 2. So block number 2 is having 0 reference, and block number 1 is having how much? Block number 1 is having, yes, anybody? Block number 1 will be having what? It will be having 3. Then block number 0 will be having what? 2. Next. Then block 3 will be having 3. So this is the new values now. Okay. Block number 0 will be having, see, only block number 2. Only block number 2 has become 0. All block number 1, block number 2, block number 3, all these have changed. They have been incremented. Suppose now new block number 5 is to be accessed. So when block number 5 is to be accessed, see, is there place here? Only 4 blocks can be stored. All 4 blocks are there. Is it not? So we are not having place for block number 5. I am bringing the block number 5 here. Which one to replace? The one which is having the value 3. The one which is having the highest value will be replaced. Block number 1 and block number 3 are having 3 here. Anyone can be selected. Okay. Anyone can be selected. So the one which is having the highest value will be replaced. So like this the least recently used will be executing. Understanding all of you? Yes? All of you are understanding? I'll explain this once again here. What we are doing in least recently used. So we have taken the example where in the cache memory we have taken the example where in the cache memory we are having only 4 blocks. So out of the 4 blocks we are giving the integer counter values 0 like that. First initially all are having zeros. Okay, initially all are having zeros. Next, if you are referencing any of the block, its value will be changed to 0. And what about others? The others, what will happen is those block whose original values are less than the block, whose original values are less than the referenced block, those will be incremented by 1. Those will be incremented by 1. Others will be kept as it is. So like this the least recently used algorithm is working. Have you understood? Have you understood? See here what they are saying. See, when a hit occurs, hit occurs means if the particular block is present already in the cache memory, the counter of that block referenced is set to 0. The block who is referenced is set to 0. Counter values originally lower than the referenced one. Now our referenced one was here block number 2. Block number 2 has its reference value 3. Who are less than 3? All you are going to increment. What you are going to do? You are going to increment by 1, and all others will remain unchanged. Okay, this is happening. Then when the miss occurs means if a new cache is required, if a new block is required and that is not present here, that time what we are going to do is we are going to load the new block into the main memory and set its counter to 0. Then which we are going to replace? The one which is having a value 3 or the one which is having the higher order value, that will be replaced. Like this least recently used algorithm will be working. Have you understood? Please reply students. If you have not understood, at least no you have to tell. Okay, only two people are answering all the while, Srivats and Venkatesh. Next, we are studying about the performance considerations. So, performance consideration means what here? We have already studied that size, speed, and cost. These are the three parameters which we are using for finding out the efficiency of a computer. But now here what we are saying, how can we increase? How can we increase the performance of the system? So first we have to find out the important measures here. There are two important factors. One is performance of a system and one is the cost of a system. See, we want a good performing system and in the low cost. So these two are the main important parameters which we have to consider for success of a computer. For successful running of a computer in the market, we have to consider these two, performance and the cost. Then we have to find out price performance ratio. Price means cost. If the cost is less, the performance is also be not good. If the cost is more, the computer is high. This is what the ratio we are having. Both of them should be actually inversely proportional, means one will increase, other will also other should also decrease. Like this it should be. It is not happening like that. So what we are going to see is how can we increase here, increase the performance. Of that we are going to see the first point, that is the first point we'll be seeing about the interleaving. What is this interleaving here is, here we are considering that the main memory is divided into different modules. First we consider that main memory is a single module. Here you can see that this main memory is a single complete module. All the data are stored in these blocks only. Okay, they are not divided. It is considered as a single unit. But suppose if the main memory is divided into different modules, when the main memory is divided into different modules, each module should be having its own address buffer and data buffer. We have seen MAR and MDR. What is that? Memory address buffer and memory data uh, register. Memory address register and memory data register, MAR and MDR. So when we are dividing the main memory into different modules, what is the advantage? First we have to understand. When we are dividing the main memory into different modules, what will happen? Simultaneously different modules can be active at the same time. So when we are dividing the work, suppose I am having a function and I'm going to divide the work into different committees. Like we are having a catering committee, we are having a decoration committee, then we are having hospitality committee. Like this I am dividing the function into different committees. All the different committees are working simultaneously at the same time. Is it not? All of them are working at the same time. So efficiency will be increased. That is why we are dividing the main memory into modules here, because the different parts of the modules can be accessed at the same time. Simultaneously we can access. So when they are active, different modules, when they are active at the same time, execution will become faster. That is why we are going to do the division of the main memory into different modules. Each module is having its own address buffer register and data buffer register, okay, which they are storing the address and the data into them. How we are accessing these modules then? So we are accessing the modules in two ways. So where we are having k bits and m bits of module number and address in the module. So to first find out the particular data, suppose I want the data like variable x. First, that variable x is stored in which module? We have to find out. For that we are using k bits of module address. So first we will find out the k bits of module address, followed by that what we are having? Address in the module. Now I found out that whatever x variable I want, it is present in the module number 0. In the module number 0, where it is present? It is present in the first line, second line, third line, last line, where it is present. So address in the module is indicated by this address m bit address module. Okay, so this is the method we are using here. So what will happen? Suppose if my data is distributed in this module number 0 and module number 1, then how do I access? So if the data is present in a single module, then that module can be accessed and can be used. Suppose the data which I require is distributed half in the module 0, half in the module 1. Then how will I access? For that, see, first module address is there, no? Like for example 4020. Next next address may be 5000. So fourth, this module address should be changed, is it not? Means what? Whenever I am telling so whenever I am saying that module number starts first, if the module number starts first, only one module will be active at that time. 4000 is starting address, so 4000 module only will be active. Next 5000 means I have to change the module number here. If the data is present in successive modules, then it will be difficult to access, because first I am having the module address, then I am having the address in the module. First k bits, then m bits. That is why it becomes difficult. If it is address is present in 4000 and 5000, so what I have to do that time? I have to change the k bits, then only I will go to the successive bits. In general, it means that only one module is active at a time. In the second method is actually called as interleaving method. What is this interleaving method? Here is, you can see here, only we have everything else is same. Everything else is same, only we are exchanging this one. Okay, we are going to exchange here. What we will be exchanging, you can see here, first we are storing the address in the module, then we are storing the module number. Okay, suppose 4099 and 5000 is my module number. 4099 is the one module, some data is present in 4099, next data is present in 5000. They are adjacent to each other. When they are adjacent to each other, see here only I can find 4099 and 5000. Means how your lower order bits are varying, no? See 11, 12, see 11, 1 1, then 1 2, 1 3. 1 is the higher order bit, it remains same. Lower order bit is the 1 2 3, it is varying. 1 1, 1 2, 1 3, 1 4. Lower order bit is varying each and every time, but higher order bit is not varying. We have to wait till it varies. So if we are having the module number as the lower order bits, then we can vary this easily. It means that multiple number of modules can be active at the same time. So this method is called as interleaving. In the interleaving, we are having the k bit module address as the lower address. When it is present in the lower address, many modules can be active at the same time. Means successive addresses can be fetched easily. So this is the interleaving. So using this, many modules are active at the same time. So work will be done very fast. When work is done very fast, what will happen? Execution also will become fast and performance also will become fast. So this is the first method where we are going to increase the performance by using the interleaving. In the interleaving, first what we have to explain here. Here the main memory is divided into different modules. Each module is having its own address buffer register and data buffer register, and the main memory generate the address in module number and address in the modules. Suppose if you want to access the successive models, if you want to access the successive modules, at that time we have to place the module address as the lower bit. We have to place the module address in the lower bit, then successive modules can be accessed easily. So this is what you are going to write in the interleaving. So next we will be seeing about the hit rate and the miss penalty. This will be continuing in the next class. Okay, so probably this may be the last topic. This will be the last topic. Then we will complete the third module. Okay, I'll take the attendance. Just wait.